Hello, grade 8 students. In today's lesson on evidence of evolution, you've been asked to read two short selections from our textbook. Some people have noted that the text PDFs that have been mailed to you are a bit difficult to read, so I'm going to read them for you and give you the opportunity to hear it as well as follow along on your own. The first selection is titled Fossil Evidence of Evolution, and you're asked to read from page 157, the section called The Fossil Record. Here it is right here. The fossil record. On your way to school, you might have seen an oak tree or heard a robin. Although these organisms shed leaves or feathers, their characteristics remain the same from day to day. It might seem as if they have been on Earth forever. However, if you were to travel a few million years back in time, you would not see oak trees or robins. You would see different species of trees and birds. That is because species change over time. You might already know that fossils are the remains or evidence of once living organisms. The fossil record is made up of all the fossils ever discovered on Earth. It contains millions of fossils that represent many thousands of species. Most of these species are no longer alive on Earth. The fossil record provides evidence that species have changed over time. Fossils help scientists picture what these species looked like. Figure 18 shows how scientists think the giant bird Titanus might have looked when it was alive. The image is based on fossils that have been discovered and are represented on the photo on the previous page. We should stop here and take a look at Figure 18. Based on fossil evidence, scientists can recreate the physical appearance of species that are no longer alive on Earth. And so we have a picture of what this animal may have looked like. And we can go back to its skeletal remains, the fossils that have been found. And I am kind of interested. I'm looking at this head with this strange sort of beaked mouth. And I'm seeing that in the image that they painted, they've kind of kept that shape there. The fossil record is enormous, but it is still incomplete. Scientists think it represents only a small fraction of all the organisms that ever lived on Earth. That completes this reading section. The second reading selection comes from Biological Evidence of Evolution, and you've been asked to take a look at pages 358 and 359. I'm going to scroll down to those. We're going to skip page 357 and come right to page 358. Comparative anatomy. Common ancestry is not difficult to see in many species. For example, it might seem easy to tell that robins, finches, and hawks evolved from a common ancestor. They all have similar features, such as feathers, wings, and beaks. The same is true for tigers, leopards, and house cats. But how are hawks related to cats? How are both hawks and cats related to frogs and bats? Observations of structural and functional similarities and differences in species that do not look alike are possible through the study of comparative anatomy. Comparative anatomy is the study of similarities and differences among structures of living species. Homologous structures. Humans, cats, frogs, bats, and birds look different and move in different ways. Humans use their arms for balance and their hands to grasp objects. Cats use their forelimbs to walk, run, and jump. Frogs use their forelimbs to jump. Bats and birds use their forelimbs as wings for flying. However, the forelimb bones of these species exhibit similar patterns as shown in Figure 9. Let's take a look at Figure 9. Figure 9. The forelimbs of these species are different sizes, but their placement and structure suggest common ancestry. We have a human, a cat, a frog, a bat, and a bird. I notice that the human has this sort of yellowish bone labeled the humerus, That's your upper arm bone, and I notice that the humerus is present in each of these animals, even though it looks very different. We also have two bones in the lower arm called the radius and the ulna, and I see that they are present in the lower arm. It's hard to see in the bat, but here they are, of all of these species. Homologous structures are body parts of organisms that are similar in structure and position, but different in function. You may remember homologous comes from the Greek prefix homo, meaning the same. And these structures are similar in that they all have the same type of bone pattern, even though they have evolved to do very different things. Anything from grabbing to jumping to flying. We're going to move on to page 159 now. Analogous structures. Can you think of a body part in two species that serves the same purpose but differs in structure? How about wings of birds and flies? Both wings in figure 10 are used for flight, but bird wings are covered with feathers. Fly wings are covered with tiny hairs. Body parts that perform a similar function but differ in structure are analogous structures. Differences in the structures of birds and fly wings indicate that birds and flies are not closely related. In fact, birds have bones, insects have no bones, and that's a key difference in these wings. Figure 10. Though used for the same function, flight, the wings of both birds, top, and insects, bottom, are too different in structure to suggest that they are closely related. Vestigial structures. The bird in the photo at the beginning of this lesson has short, stubby wings, yet it cannot fly. The bird wings are an example of vestigial structures. Vestigial structures are body parts that have lost their original function through evolution. The best explanation for vestigial structures is that the species with a vestigial structure is related to an ancestral species that used the structure for a specific purpose. The whale shown in figure 11 has tiny pelvic bones inside its body. The presence of pelvic bones in whales suggests that whales descended from ancestors that used legs for walking on land. The fossil evidence supports this conclusion. Many fossils of whale ancestors show a gradual loss of legs over millions of years. They also show at the same time that the whale ancestors became better adapted to their watery environments. Figure 11. Present-day whales have vestigial structures in the form of small pelvic bones. We're given this diagram. The species is Ambulocetus notans. Ambulocetus is literally Latin for walking whale. I wonder why they called it walking whale. Between 50 and 60 million years ago, this mammal breathed air and walked clumsily on land. It spent a lot of time in the water, but swimming was difficult because it had legs. Individuals born with variations that made their rear legs smaller lived longer and reproduced more. This mammal is an ancestor of modern whales. The front appendages were flippers, but these were still leg-like structures. Below it, we have a modern toothed whale. You can think of this, maybe you recognize the silhouette of a killer whale. You'll notice it has a vestigial pelvis in this area. Ambulocetus still had a pelvis, but it had legs. You'll notice there is no leg on this toothed whale. After 10 to 15 million more years of evolution, the ancestors of modern whales could no longer walk on land. They were adapted to an aquatic environment. Modern whales have two small vestigial pelvic bones that no longer support legs. And of course the question is, why would the whale have a pelvis or parts of a pelvis if it had no legs on its body? The answer, of course, being that the legs evolved out of an ancestor over time as the whale became better adapted to the water. That's the end of our reading today. I wish you luck with the questions that are located in the other document attached in Google Classroom.